Welcome to this video. My name is Mark Scythian and the date today is May 8th, 2025. So this lecture is going to focus on a projectile intercepting a falling object. So we will actually use something a little more durable and robust for this type of application. So this will be a 500-pound object dropped from 5,000 feet altitude, and we want to intercept the object at 500 feet above ground level. So we'll use a Howitzer cannon, which is its barrel end is positioned 12,000 feet from ground zero below the projectile, and we're also going to ignore the aerodynamic drag because the final velocity or its interference with free fall drop time or gravity drop is negligible. This also includes calculating the free fall time from 5,000 feet altitude to 500 feet altitude. So we can use the delta d sub y, or the vertical distance, change in vertical distance, delta d sub y right here is equal to 1/2 gt squared. So if we were to take the difference from 5,000 feet to 500 feet, we have a delta dy of 4,500 feet, for which we convert to meters, and then we simply equate it to the 1/2 times gravitational acceleration. Little g is the gravitational acceleration on Earth, which is 9.81 meters per second squared, times t squared. So if we just solve for t squared, we would then get 279.7, and its square root will solve for the time. So square root of t squared is t, and the square root of the 279.7 becomes 16.7 seconds. So now we have the free fall time it'll take the object to reach 500 feet above ground level. So we can convert the range of 12,000 feet from the cannon's end to meters. And just a few notes here that we could use the conservation of energy, the potential energy, gravitational potential energy, mass times gravity times height is equal to kinetic energy, 1/2 mass times velocity squared. And then we were able to calculate the velocity at 500 feet. We could do that, but it's not relevant to the projectile intercept of a falling object application. And then also, if we were trying to find the flight time of the projectile to make contact with ground zero, we would have to know the height of the barrel off the ground. So in this case, it's not drawn to scale, but let's say it is a practical 12 feet above ground level. We would have to then account for the gravity drop for what it would take at a constant velocity from our 500 feet to some place at the ground, but that's not what this model is looking for. So the 12 feet becomes irrelevant. We need the initial velocity of the projectile, so that's a M777, let's say we're using, that's 2170 feet per second, initial velocity v sub o, and then it's placed 12,000 feet. So this would be a practical application for tracking an object at a certain specified altitude and then firing at a certain theta angle, cannon launch angle, with respect to the horizontal, to then make the round intercept the object. So we can continue on solving the rest of this model. Next we have the projectile range formula. That's the initial velocity squared times the sine 2 times the launch angle theta divided into g. So we can just take the meters range and make this equal to the initial velocity in meters per second, so 661.6, then times the sine 2 times theta divided into 9.81. So if we solve this algebraically, we can then solve for the theta value. So we would just equate the output to the output times the denominator, so we can have a one-line equation without the fraction, and then solve for 661.6 squared times sine 2 theta. So if we were to just divide and algebraically solve for sine 2 theta, we could then simplify it by dividing both sides by 2. So we get half of our ratio equal to sine theta, and then we just get the inverse sine of the value 0.041. So we get a launch angle of 2.35 degrees approximately. Now, something this precise will have to have multiple decimals in the thousandths or 10,000ths on the angle. And we're also adjusting somewhat for drift and three-dimensional crosswinds, but relatively high launch velocity, and we come very close to making a direct kinetic impact with the object. So again, we have to test this in the range formula and make sure that it comes to 12,000 feet. And so we have a little problem here. We're off by about 9 meters or 8.2 meters. So this is going to be a problem. It's probably going to be a miss. So we put a little X there as subject to readjustment. So if you take a little time or even graph the equation or use the linear regression or even trial and error, you can get a more precise launch angle of 2.35162. So if we put this back into the equation, we're going to get a precise versus precision versus accuracy, so a more precise calculation, and then we could do the rounding. But if we multiply this meter value times 3.28 feet to a meter, we get 12,000.03 feet. So we can clear that as the right angle. So the aiming information and data would have to be in the, say, tenths, hundreds, thousands, 10,000s, 100,000s of degrees for accuracy. And this increases the probability for a direct hit. And of course, there are three-dimensional ballistic computers that do pick up wind data and then make servo transducer oscillation corrections on the z-axis or the turn axis, we'll say like that. So now we're dealing with the y-axis for launch angle, and X would be irrelevant. That would just be the plane or the axis of the projectile motion. And since really it's the gravity that alters the range of the projectile, we spin the round through the rifle barrel, and then we have a relatively constant velocity from the initial to the final, because as we gain parabolic ascent on the trajectory or the parabolic projectile motion, it behaves as a quadratic function. So it will go to the top of the symmetrical parabola and then come down basically at the same speed as the initial velocity. So more or less there's no change in the velocity with projectile motions, more or less. So of course we do have a stop in the vertical velocity just momentarily at the symmetry or middle point of the parabola, but we're focusing on the relevant information, so that's not relevant. We don't want to solve for the maximum height, which there's another projectile equation to do so. So we have all the relevant information, and so then we've come between a or relatively accurate launch angle degrees in the tens and 100,000ths of decimal points. So therefore, next we have to figure out what the flight time is of this trajectory from the launch of the barrel to the target point, the object intercept. So we can use this formula here, 2 times the initial velocity times sine theta, or the sine of the launch angle, 2.35162 degrees, divided into gravitational acceleration on Earth. So if we work this out, we get 2 times 661.6, and again, it's not squared for the time of flight equation. So it's 2 times 661.6 times the sine of 2.35162 degrees. And then we divide that into 9.81. So we get a flight time of 5.52 seconds, or 5.5 seconds. 5.5 seconds is the value we get there. So this means we're going to have to subtract, because these are values that are constants. They're kind of etched in stone based on the rules of physics on Earth. So what we can do to make a strategy, a protocol, we can subtract the time of flight of the projectile from the free fall time of impact, 16.7 seconds, and get 11.2 seconds. So this then allows us to solve the problem and more or less intercept the falling object from a considerable range. And the solution slash directions or directive is 11.2 seconds after falling object descends from 5,000 feet altitude. Cannon is fired at a cannon launch angle of 2.35162 degrees. So whenever the object is tracked at 5,000 feet, the cannon operator would have to wait 11.2 seconds and then fire the cannon, and then 5.5 seconds later, the projectile, the red here, would make contact with the object and intercept it or destroy it before it hits the ground. So these are just other applications in projectiles, kinematics, dynamics, and with or without respect to thermodynamics, which we could use a lot of different models to develop potential energy, but this particular lecture is just focusing on the projectile intercepting, the projectile interception of a falling object. Thank you for watching this video lecture, and have a great day.